All right, guys. So we finished talking about um, chemical energy and enthalpy associated to chemical reactions, and the next period of time we're going to be start to um, taking a microscopic view on atoms and molecules, and we're going to focus on um, how the electrons within atoms are distributed, and also how does that particular effect affects atoms' behavior when they start to make chemical compounds. Okay, and we've talked about atomic symbol and atomic theory at the beginning of semester. Okay, and back then we already know that atoms are generally made up by a nucleus and different numbers of electrons, and those electrons are going to interact with other atoms, and the result is that you ended up getting chemical compounds. Molecular compounds are formed when you have atoms sharing electrons, and ionic compounds are formed when you have atoms losing and gaining electrons, and then the positive ions and negative ions resulted from that having electrostatic attraction between each other. Okay, but how are the electrons behaving, and why would they behave that way? Okay, now that we know a little bit more chemistry, we're going to take a deeper look about it. And since that's our topic, you'll probably be a little bit surprised with where we started on this part, because we're actually starting on the topic of properties of light and electromagnetic radiation. You just told us you're going to be discussing with us about atoms and their electrons. How does light have to do with this? Okay, the reason we're starting to from this point is because this is the beginning of people start to know what's in atoms and how does the electrons behave. Okay, light is the tool, light is the path that lead people to the understanding of electron behavior between within atoms. Okay, and as we go further, you will start to see the connection between them. All right, so first of all, we know what light is, okay, but what is a electromagnetic radiation? Okay, electromagnetic radiation is consist of oscillating electric and magnetic fields which are perpendicular to each other and to the direction of radiation propagation. All right, so sounds like a pretty complicated concept, okay, and also have lots of sciencey kind of words, and you guys know I'm not big on memorizing the definition, okay, yeah. And we're more focusing on understanding and being able to kind of picture exactly what this is, okay. So first of all, oscillating, okay. Now at this point after your high school education, I believe that everybody have a little bit of idea of what electric field and magnetic fields are, okay. And oscillating means going back and forth, okay. In a sense, oscillating here, when it comes to electric field and magnetic field, okay, is saying that your electric field and your magnetic field is constantly changing, okay. It's changing in the form of kind of a wave. I hate drawing on this. Okay, so then this type of radiation, and light is one form of it. Okay, light is a particular type of electromagnetic radiation. Okay, so all electromagnetic radiations are made up by electric field and magnetic fields. Okay, that works like waves. Okay, constantly, gradually changing. Okay, back and forth. And now, let's say this is a beam of light. Okay, we know light goes from one spot to another, so it has a propagation direction. Okay, so this arrow is showing how this light is moving forward. Okay, now, and this wave that I just drew here, and you can see this is perpendicular. Okay, what do you mean perpendicular? 90 degree. Okay, with the direction of your radiation. Okay, and let's say this is my electric field. Okay, now, then you also have another wave, okay, which is the magnetic field. Okay, and this time it is perpendicular, it is 90 degree. So, kind of like this. Now, this is, you can imagine this as kind of the same wave, but if you turn the plane of the electric field 90 degree inward, okay, spin it along the radiation direction axis, spin it 90 degrees. Okay, what you got here is the magnetic field. Okay, it's also a wave, but it's 90 degree to the electric field, and it's also, as you can see, the same way perpendicular. Okay, so if you have to do this, then this angle here is actually, okay, a 90 degree angle. Okay, so this here is a 90 degree angle to the radiation direction. Okay, every electromagnetic radiation are kind of made up like this. All right, and now because electromagnetic and magnetic radiation, okay, is kind of having this waveform. Okay, so all electromagnetic and magnetic radiations have what we call the wave properties. What are the wave property? We have things called wavelengths, and we use lowercase Greek letter lambda to represent it. Okay, what is wavelengths? Wavelengths is the distance between two successive peaks. Okay, so the distance between two peaks is the wavelengths. Okay, and since it's distance, so it has the unit of centimeter, millimeter, meter, or kilometer, or if you want a small micrometer, and so on and so forth. Okay, now another wave property is called frequency. We use Greek letter nu, lowercase again, to represent it. It looks like a V, but this is number of peaks that passes by a fixed point per unit of time. Okay, so kind of like you're throwing a small piece of rock into a pond. Okay, once you throw it in there, you see the wave, right? And the wave is getting to the bank of the pond, and now you can have a stopwatch and you can count, okay, in 1 minute, okay, how many waves, okay, hit the bank, okay, and that number, okay, in 1 minute of time, okay, is the frequency of the wave that you created with that small piece of rock. Yeah. And of course, in science, when it comes to electromagnetic radiation, okay, more likely you're using the international standard time unit, which is second instead of minutes or other time, okay, and so since frequency is number of peaks, and number of peaks doesn't have a unit, okay, just counted number, so, or calculated number if the frequency is not something that, like for example, electromagnetic radiation frequency is not something that you can count the peaks. But anyway, the unit of it would be 1 over whatever time unit you use, and most likely it's second, okay? Or you can write it as second to the negative first, okay? And this unit, if it looks new to you, I'm pretty sure you have heard the official international standard unit of frequency, okay? 1 over second is also defined, okay, named after a scientist. It's also called hertz. Okay, hertz means, or in short, Hz. Okay, hertz means 1 over second. Okay, and of course, if you want, you can do 1 over minute, 1 over week, 1 over year, whatever. But 1 over second is the international standard. Okay, now, and whenever you see, let's say you listen to a local radio station. Okay, and for example, all the radio station, when they broadcast, okay, they're by law required to, tell people about, okay, their one of the about identify themselves, and one of the local radio station, okay, and the one that I believe broadcasting WVU football games and stuff like that, okay, on the radio identified them as 102 WVAQ. Okay, what does that mean? Like, don't worry about the letters. The number is the one that matters here. The number is telling you where you can, which frequency you can find them. This is a FM station. Okay, 102 means 102 megahertz. So if you turn on your radio and you turn it to frequency of 102 megahertz, you would find the radio station. And what does 102 megahertz means? Mega is 10 to the 6 power, okay? So that means it has the radio wave this radio station use have a frequency of 1.02 or 1 times 10 to the 8 or 102 times 10 to the 6, okay, hertz. In every 1 second, the radio wave these guys use, this station use, okay, is going to send 102 million peaks through a given fixed point. Okay, so you can imagine, okay, 1 second, 102 million peaks. So that's what frequency is standing for. Okay, and another wave property that we're not going to talk too much about here, we're not going to be focusing on here, is called amplitude. Okay, and this means for a wave, the height of peaks. Okay, and now this is used to represent a lot of time the strength of the wave. Okay, but this is also where for radio waves, okay, outside noise, okay, outside influence can change the amplitude of the wave. We're not worrying too much about this particular concept in our discussion because it doesn't have much to do with the chemistry content the wave property of radiations is related to. All right, now, wavelengths has unit of distance, okay, international standard being meters. Frequency have the unit of 1/second, okay. If you multiply the two together, okay, both using international standard unit, you would see that this ended up being meters times 1/second, and you ended up getting meters per second. Well, let me ask you this. What is the unit of meter per second? We've all seen this unit before at some point, okay? And this is a speed unit. In 1 second, how many meters did you move? Meters per second. Okay, so what does that tell you? Wavelengths times frequency gave you the speed of the radiation. And for the speed of radiation, we use a specific letter to represent it. Okay, and let's be careful with the letter that we use. We use lowercase c to represent this. Now, why do you need a specific letter to represent this? Because all electromagnetic radiations have the same speed. In vacuum. And that speed is therefore called the speed of light, because light is one particular form of electromagnetic radiation, and all electromagnetic radiations have the same speed. Okay, and the speed of light, they all have this speed in vacuum. Yeah. We have a way more accurate measuring at this point with the technology that we have, but for the purpose of this class, we're going to use an easier number. We're going to say it's 3.00 times 10 to the 8th meters per second. Okay. So what does that mean? This means that every second, okay, the electromagnetic radiation can travel about 250,000 miles. Okay, a little less than 250,000 miles. Okay, about 200, a little less than 200,000 miles per second. Okay, and about circling the Earth on the equator for about 8 laps. Yeah. All right, so now if wavelength times frequency equals the speed of light, which equals the 3.00 times 10 to the 8th power meters per second. What does that tell you? That means I don't need to know for a given electromagnetic radiation, I don't need to know both of the wavelengths and frequency. All I need to know is one of them. Okay? If I know one, I can definitely use the speed of light to calculate the other. Okay, so here's an easy example here. A local radio station broadcast at 91.7 megahertz. Calculate the wavelengths of radio wave used. Okay, so since wavelengths times frequency equal to speed of light, so wavelengths should equal to speed of light over frequency. So 3.00 times 10 to the 8th meters per second, and 91.7 mega means 10 to the 6. Hertz is 1 over second, so second cancel, and that you ended up getting meters, and that result is 3.27 meters. Okay, and now, kind of off the topic, talking about trying to relate this to everyday life a little bit, and we talk about radio wave here, okay? And I don't know if your generation, my students' generation at this point, okay, how much radio you would ever listen to, or if you even have a radio to listen to us. But I believe cars still have radios installed in them. Okay, maybe you don't listen to it, but typically the radio you listen to. Okay, I'm not talking about satellite radio. Okay, that's a different animal. Okay, but the regular radios, you've heard about FM and AM. Okay, and a few things you may or may not know at this point is that FM, okay, is the stereo radio. Okay, the signal is much better. Okay, if you're listening to radio and you're listening to music, you probably want to listen to it from FM because it has less noise. Okay, and it also gave you better listening enjoyment. Okay, like music sounds better in FM. Okay, AM you probably use it to listen to news or and now the FM means frequency modulated. Okay, AM means amplitude modulated. Okay, the major difference between the two, okay, comes on the frequency. Okay, FM radio usually have the frequency around 100 megahertz. Okay, AM radio usually have the frequency around 1000 kilohertz. Or if you put it together, once K is 10 to the third, and 10 to the third times 10 to times 1000 10 to, so it is about 1 megahertz. Okay, higher frequency, lower frequency. Yeah. And now, let me ask you this: high frequency means what? Between frequency and wavelengths. Okay, this is much lower wavelengths. Okay, and the AM radio, their wavelengths is about 100 times compare. Their frequency is about 1% of the normal frequency of FM. Okay, and that means their wavelengths is about 100 times. Okay, so higher, or longer. Wavelengths. Okay, and they are different kind of pros and cons for each. For example, the FM, the frequency modulated radio signals, okay, they are less likely to have noise. Okay, AM amplitude is more likely to be affected by noise. Okay, and now AM radio wave covers more range. It's less afraid of a barrier. Okay, FM radio actually can be blocked easier. Now, why? Well, look at this FM wavelengths. Okay, wavelengths is around 3 meters. What does that mean? Well, if you have a large building, okay, that's in this range, let's say 50 meters long, okay, and going under the building, okay, it can easily block, okay, your FM signals. This is why if you're listening to FM radio and driving in a city block, okay, you could be getting in and out of the radio would be getting on and off, okay, as you drive through a city block. And AM, because it has huge, like 100, like instead 3 meters, maybe 300 meters of wavelengths, okay, you don't like, it's not likely that you have a building, okay, a single barrier that has that size within the city. So it's harder to block. Anyway, so you don't need to memorize any of this radio talk that I just talked about. I just like to kind of relate real life type of examples with the things that we're learning in class. Now, all right, so now we understand the relationship between wavelengths and frequency. And now, another thing that is also very important for us to understand the electromagnetic radiation and light is that, well, we know this. Energy is always associated, okay? Any electromagnetic radiation is always associated with different amount of energy, okay? And how much energy is associated with a given radiation, okay? That value can actually be calculated using the equation of E equal to h times nu. H here is the Planck's constant. Okay, which has the value of 6.626 times 10 to the negative 34th joule second. Okay. And I believe that we said at the beginning of the semester when we first introduced the Avogadro number, we said that Avogadro number is probably the biggest constant that you would see in this class. And if that's the case, well, Planck's constant is by far the smallest constant that you're going to see in this class. Okay, and look at the 10 to the negative 34th. Okay, and now, of course, you look at this number, you go, this doesn't sound right. Okay, now, your frequency, let's say radio wave and whatever, okay, the frequency is something times 10 to the 8th hertz. Okay, you multiply that with this extremely small Planck's constant, okay, the second is going to cancel, and then you ended up getting an energy of something times 10 to the negative 20th something power joules. I mean, that doesn't sound right, does it? We know this for a fact, that all the energy on Earth, okay, ultimately is coming from the sun, right? How do we get the energy from the sun? Sunlight, electromagnetic radiation. And whenever we're talking about, petroleum energy, coal energy, we know all of those are from plants and or animals or whatever, okay, from ancient time. But those energy, we've calculated amount of energy, okay, from a fuel before. It's like thousands of kilojoules of energy from burning 1 mole of a fuel. And we have millions, billions of mole of fuel on Earth, and you're saying they all come from energy of like 10 to the negative 20th something joules? That doesn't sound right. Okay, so let's make something clear. Okay, yes, the energy of the sun is coming from the energy of all the energy on Earth is coming from the sun ultimately. And yes, okay, we have a lot of energy. It's not just joules, it's kilojoules, megajoules, however you like. But it's my answer is also going to be yes when I say, well, this represents the energy of a given electromagnetic radiation. That extremely small number that you're going to calculate and get, it's true. Okay? But let's be very clear. The h nu here, this here, calculation here, this represents a what do we call individual packet of the radiation energy. And each beam of light, okay, every radiation, each is made up of numerous energy packets. Okay. A beam of light, and this energy packet, we gave it a name. We call that, we say this is a photon. Okay? And now, each beam of light, each beam of electromagnetic radiation is made up by numerous photons. Okay? One photon may be having a very, very small amount of energy, but when you have billions, okay, trillions, gazillions of those photons, now you have a lot of energy. Yeah. All right, so to clear up our understanding about that equation, let's do a quick calculation example here. Calculate energy of a green light photon with wavelengths equal to 560 nanometers. Okay, so energy should equal to Planck constant times frequency. Okay, but I don't have frequency, but it's easy. Frequency is also speed of light over wavelengths. So not only energy of a photon can be calculated from h nu, it can also be calculated from hc over lambda, over wavelengths. Okay, so plug my numbers in, 6.626 times 10 to the negative 34 joules second times 3.00 times 10 to the eighth meter second. So second cancel, divide by wavelengths, 560 nanometer is 10 to the negative 9 meters, so that cancel. And of course, you got only joules left. And this calculation gave you 3.55 times 10 to the negative 19th joule. Okay, so that would be the energy of one single green light photon. Okay, that seems like very little energy that wouldn't be able to do nothing. Okay, but what if I have a lot of these photons? If you have, let's say, 1 mole of green light photon, then how much energy are we talking about here? So then you would have 3.55 times 10 to the negative 19th joule multiplied by, well, Avogadro's number, 6.022 times 10 to the 23rd. Okay. And this calculation will give you 2.14 times 10 to the 5th joule, or 214 kilojoule. Okay? So, one photon, it might not be a whole lot of energy, but if you have a lot of photon, okay, then that energy could accumulate. So if you're wondering, well, if green light has such a low energy associated to it, okay, but on the other hand, you can have lasers, okay, which is different color of lights, right? That can cut metals, can burn holes on walls. Why? That requires a lot of energy. Well, a laser is going to be a focused beam of light that contains numerous photons. And if you can put, okay, moles and moles and moles of green light together, you can see each mole 214 kilojoules of energy. That's a lot of energy. Okay, and if you have moles after moles after moles, now we're talking about cutting metals, burn through walls, and stuff like that. So energy associated to a photon is a very, very low number because the low value of Planck's constant, but you can always have more. All right, so of course, once people start to have this standard, okay, like frequency, wavelengths, and energy associated, now people are trying to look at different type of electromagnetic radiations, okay, and the electromagnetic radiations that people know at this point, we can all put it into what we call a electromagnetic spectrum. Okay, and it goes like this. So this is my spectrum. Okay, right in the middle, a very narrow region is what we call, you can put VIS here. This is the visible light. This narrow range contains all the different colors of lights your naked eye could ever see. All right? And this is in the middle of the electromagnetic spectrum. Okay? And the wavelength is around 560 nanometers, give or take. Okay, from about 300 something nanometers to 700 something nanometers. Okay, and then let's say the energy is increasing from left to right, this direction. So on the left of the visible region, okay, you're going to have, what do we call, ultraviolet, UV. Okay, this is what you put on your sunblocks in summer in summer for. Okay. Why do I need to? Why do I enjoy a sun bath, but I want to put sunblock on my body? It kind of seems like contradicting. Well, you're blocking the UV radiation in the sunlight. Okay. Why do you want to block it? Because it's much higher energy compared to visible light. Okay. Visible light can maybe tan your body and kind of help your metabolism of the body. But UV light can do damage to your skin. It can long-term exposure would give you skin cancer. Okay. Too much energy. Okay. And then beyond that, okay, the X-ray that you take at hospitals is also electromagnetic radiation, and it's a much higher energy one than even the UV. Okay, this is why, okay, whenever you go to take an X-ray, okay, the radiologist would put on some kind of a heavy vest. Okay, back in the days, 30 years ago, it may be like lead board, okay, to block the X-ray. Nowadays, they have more advanced material, so it's a little lighter, but you still need to put that vest on. I'm only taking one over let's say you go to a dentist, you take an X-ray, okay, I'm only taking this on my teeth, okay, so my body, my neck, my chest, I want to put that vest on and protect it, okay, I don't want to get X-ray too many times, okay, your health is in trouble, okay, so that's why radiologists are very, very careful with it, and the reason of that is associated to the high energy of X-ray. Okay, and then beyond X-ray, okay, is what we call gamma ray. Okay, and what's gamma ray? The highest energy electromagnetic radiation. Okay, people know at this point are all put into the gamma ray range. Okay. How high energy? Well, remember, if I don't know if you heard about this, you should. Whenever we send a satellite, okay, to the outer space, okay, what's the biggest damage, okay, to satellite? Okay, cosmic rays in the space. What's cosmic ray? Gamma ray. Okay, why is it damaging? Because very high energy packed. Okay. Now we do use gamma ray to our advantage nowadays. Okay. For example, okay, in some surgical area, okay, people nowadays start to use gamma ray knives instead of scalpels. Okay. Instead of using a metal blade to cut you open, okay, we could use a gamma ray knife, okay, a gamma ray gun or whatever you want to call it, okay, to cut you carefully in a surgical process. Why? What's the benefit? Well, when a metal blade, okay, cut your skin open, okay, you will bleed, okay, and you'll try to stop it because, well, for obvious reasons, okay. But for gamma ray knife, the nice part is it's not really cutting you open on your skin. It's kind of burn you open. Well, you made it sound worse. Well, not exactly. Okay, as it cut you open, the high energy resulted in kind of high temperature momentarily. And that high temperature, as your skin is being cut open, okay, for the surgical need, okay, actually that high temperature momentarily kind of burns shut your micro veins in the skin, and that stops you from bleeding too much. Okay, so highest energy electromagnetic radiation form is gamma ray. Yeah. All right, so for the visible range, okay, on the end where it connects to UV, okay, UV means ultraviolet, right? So the edge of the visible is actually the violet color, okay, and that's the high energy end or high frequency end, because energy and frequency are proportional. So high frequency end is violet of visible region is violet. What's the low end of frequency? It's the red end. Okay, what's in beyond the red end? We're going to continue that on our next lecture.